Now let's look at the case when it's not just free oscillations, but there is an additional external force applied to the spring mass system. Usually, this external force is a periodic function. For example, it can be like cosine of omega t. And the differential equation that we are going to get is like this. The left-hand side is still the old one, but the right-hand side, now instead of 0, we are going to get this external force. So let me show you how it looks like, right? So in this case, note that I've set the frequency of the driving force to be less than to be more than the frequency of the spring mass system. So this kind of thing here on the left is our driving force, and this is our spring mass system, and here is what it looks like. So applying an external force means that we are essentially, it means that the spring is not fixed, but we are trying to mess around with the spring itself too. So note that I think it's pretty clear that the natural frequency of the spring, so the weight here, it oscillates slower than the driving force. So you can try to change it, say to when the natural frequency of the spring mass system is mod. So then I think it can be seen here, right? So that the weight here goes left and right faster than this rotating thing. Well, and then maybe since we are on it, you can see what happens if the frequency of the spring mass system is exactly the same as the frequency of the driver. Then when the spring goes right, the force pushes it right further, and when the spring goes left, the driving force pushes it left even further, and so on, and then the amplitude increases, and that's what's going to happen. So, but let us now assume that the frequency of the driving force is different than the natural frequency of the spring mass system, right? So the general solution on how do we solve the non-homogeneous equation? So we need to find the general solution of the homogeneous equation first, which we know. So by the way, maybe here, this is important. So that omega naught is square root of k over m, so which means that if you take omega naught squared, you're going to get k over m. So m omega naught squared minus k is going to be 0. You will see why this is important in a minute. So then you can compute the Wronskian of these two solutions. You see that it's just the same as the frequency. Now, a little challenge for you is to solve the non-homogeneous equation using variation of parameters. What I'm not going to do it, I'm going to just guess. Okay. So how do I guess? Let me just explain. So we are going to try. Maybe let me do it here. So I mean, if the right hand side has cosine of omega t, then well, it's natural to try u in the form of cosine of omega t, maybe with some coefficient. So let me write coefficient c. And so then let us substitute it to the differential equation. So then we're going to get m u double prime. So whenever we differentiate with respect to t, then one extra omega is going to come out. Then I'm going to have m omega square times, well, c is going to be here, sorry, and minus sine, of course, cosine of omega t plus k times c times cosine of omega t equals f naught cosine of omega t. Then cosine of omega t is going to cancel happily, and then we can just solve for c. So the left hand side is c times minus m omega squared plus k equals f naught. So c equals f naught. Well, I will write minus f naught over m omega squared minus k. So which means that a particular solution is given as minus f naught over m omega squared minus k cosine omega t. Well, so same thing here, but note that this is not going to work if omega equals omega naught. So why? Because if omega equals omega naught, then the denominator here is going to become 0. Right? And then this formula does not work. So which is why it only works when omega is different from omega naught. And so then we have the general solution of our differential equation. And you see it is a combination of oscillations with frequencies omega and omega naught. So there are two different frequencies, and if you plot, it's going to be some kind of periodic function. Well, it is periodic if the ratio between omega and omega naught is a rational number. If it is irrational, then it's going to be a bit chaotic. But anyway, it's going to be a series of oscillations. So here is the answer. And here's a couple of examples. I'm not sure how to describe these examples. So, well, anyway, in this case, the ratio of these two frequencies is 5, and you kind of see it, right? So then there is the general trend, which is less frequent, so it corresponds to frequency 1, and there is this trend which is more frequent, it corresponds to 5. Well, in this case is kind of similar to, so there is this general trend which corresponds to frequency to less frequent oscillation, and there is this trend around, well, motion around it, which is more frequent. And I suggested you, I'm not going to do it, but I suggest that you click here and play with it a little.